This is an example on how to calculate Mohr's circle, how to draw Mohr's circle for a stress element. Sometimes it's a little confusing for students new to this when you see negative stresses, so I've decided to use that as the example here. We've got a negative normal stress on the x face of minus 2,000 psi. We've got a positive normal stress on the y face of 1,000 psi. For the shear stress on the x face, we've got 1,000 psi in the positive direction. Now, one of the requirements of the stress element is that the shear stress on the y face be equal and opposite to that on the x face. If they're not, then there's going to be a net moment on the stress element, and it's not going to be in static equilibrium. So if we know one shear stress, we know the other one by default. Now, here's the axes we draw Mohr's circle on. It's normal stress and shear stress. This is different than you're often used to. These are not geometric axes. These are stress axes. The reason these are like this is that Mohr noticed when you write out the equations for how to transform stresses by rotating a stress element, that the resulting equations look like the equations for a circle. So if you plot them on these particular axes, you get a circle. This turns out to be extremely handy. It's a nice graphical way to do things. The big picture, the important thing about Mohr's circle is it lets us calculate maximum and minimum stresses without knowing necessarily beforehand what angle they're at. We pick x and y axes really for convenience. If we calculate stresses on a part, we're going to set up some coordinate system that's maybe aligned with one of the axes of the part. There's no reason to think that the coordinate system we pick just for convenience is the one along which the stresses will be a maximum or a minimum. That's where Mohr's circle comes in. If you know sigma x, sigma y, and tau xy on any coordinate system that you pick, you can transform that and find out what the maximum and minimum stresses are. So let's start by doing this. We're going to plot 2 points on our coordinate axes here, our stress axes. The first one is what happens on the y or on the x face of the stress element. We're going to pick minus 2,000 and 1,000 as our points. Okay, and that's just a location on this plot. So I'm going to go minus 2,000 over, and I'll get my head out of the way here in a second. Okay, that line is at sigma equals minus 2,000, and I'll come over here. So there's point number 1. That's the data from the x face of the stress element. Now, next point we're going to plot is sigma y is minus, there's positive 1,000 and tau xy is minus 1,000. So this is going to look like this. That's point number 2. That's going to be from the y face. So I go over 1,000 here in the positive direction and down 1,000. And that's data from the y face of the stress element, right? Step number 2 now is to figure out where the mean normal stress is. We're going to draw a line from here down to there, and it's going to cross right about there. Sigma bar is just the average, sigma x plus sigma y. In this case, it's minus 500 psi. Right? So this point right here, sigma bar, and that's 500 psi. That's the center of my circle. If you know the radius and the center of a circle, you know everything there is to know about the circle. The way this is set up, the circle will always lie along this horizontal axis. It will be centered on the normal stress axis. Really all we're doing when we're figuring out how to draw Mohr's circle is we're figuring out where the center should be in this horizontal direction and what its radius should be. Well, we now know where the center is going to be, right there. Next thing we need to do is figure out the radius. Well, let's just say right there is going to be the radius. I know that's 1,000, and I know that's 1,500 now. comes out to 1802.8 psi. That's the radius. Now we can start drawing the circle here. Let's see if I can do this here. I'm going to just eyeball this thing. There you go. That distance right there is tau max. Tau max is the radius of the circle. All I've done is taken this and rotate it up that way. That equals 102.8 psi. So the maximum shear stress at this point in whatever part this might be is going to be 1802.8 psi. Now, what's the minimum stress here? That's going to be the location of sigma bar minus the radius. Right? So that's going to be minus 500 minus 1802.8. So that's going to come out to minus 2302.8 psi. Compression. What's the maximum stress now? I can continue that circle right there. Maximum normal stress is right there. Sigma max is now going to equal sigma bar plus the radius. So it's minus 500 psi plus 1802.8, and that works out to 1302.8 psi. That's the maximum. That's the tensile stress. It's the maximum tensile stress. This part we'll see. The last thing to figure out is what direction does this occur in. If we look at that, that's going to be 2 phi. Right? This is the twice the angle I'd have to rotate the stress element so that the x face would see that stress. Right? And if you look at if you do the trigonometry, 2 phi is the inverse tangent of that divided by that. So it's 1,000 over 1,500. 2 phi equals, make sure I get this right, 33.69 degrees. So that phi equals 16.845 degrees. So if I rotate this stress element 16.845 degrees counterclockwise, the x face will see that stress. Now, if I want the x face to see the maximum shear stress, I just use that angle, and that's 2 phi prime. 2 phi prime plus 2 phi equals 90 degrees.